We drilled into the moon, and it blinked back. In the 2040s, a gravity probe found a perfect sphere, 50 kilometers wide, buried deep under the lunar South Pole. It wasn't a cave. It wasn't rock. It was a region where the moon's gravity went wrong. How do you hide a piece of impossible physics inside our nearest neighbor? And what do you do when it starts sending messages back? In the late 2030s, a mission called the Lunar Quantum Imager, LQI, went up. It wasn't built to hunt for aliens. It was built to hunt for lumps. Instead of cameras or radar, it carried gravimeters, atom interferometers, clouds of ultra-cold atoms dropped in freefall, their quantum waves shifting with tiny changes in gravity. Think of them as gravity microphones, listening to how the moon pulls. Dr. Aisha Karim ran the mission. She'd grown up in Karachi, watching grainy Apollo reruns on a flickering TV, imagining the moon shining above her when the power went out. As a planetary geophysicist, she specialized in mascons, mass concentrations under the lunar surface, dense patches left over from ancient lava seas and titanic impacts. Her job with LQI was to map those mascons with unprecedented precision. Instead, she found a hole in gravity. Under the South Pole Aitken Basin, the biggest impact crater in the solar system, LQI detected a gravity deficit. Not a fuzzy patch, but a mathematically sharp, perfectly round region about 50 kilometers across. The mass inside was significantly less than lunar models allowed. Aisha ran every check she could think of: thruster logs, noise models, solar radiation pressure, instrument calibration, even obscure quantum phase unwrapping issues in the atom interferometer. The sphere stayed. It behaved like negative excess mass, not empty space, but something that cancelled out some of the moon's normal gravity. In general relativity, you can mimic that kind of effect with exotic configurations, negative pressure, concentrated vacuum energy, the sort of things theorists invoke for warp drives and wormholes. On paper, they were fantasies. Until the moon started acting like it was hiding a patch of impossible space-time. On Earth, deep underground, huge neutrino detectors like Super Kamiokande had been watching for ghost particles, neutrinos from the sun and distant supernovae. Neutrinos fly through whole planets as if they're not there, but once in a while, one hits a detector and leaves a tiny flash. The pattern of those flashes can, in principle, tell you about the insides of stars and planets. Neutrino tomography. Usually the moon barely registers. It's too small and low density to change the solar neutrino flux much. But when Aisha cross-correlated LQI's orbital passes with archived neutrino data, she noticed a rhythm. Every time that south polar region swung between Earth and Sun, neutrino counts dipped slightly more than expected, as if neutrinos passing through that exact internal zone were being bent, nudged off their paths like light through a lens. Somewhere deep under the lunar surface, something had been quietly refracting neutrinos for billions of years. We thought we were scanning the moon. Maybe the moon was scanning us. By the 2040s, the Shackleton region near the lunar South Pole had become a small town. Artemis Shackleton Base sat on a ridge of peaks of eternal light, solar arrays shining across most of the year, while nearby craters held water ice in permanent shadow. Commander Marcus Reed, a former test pilot turned lunar base manager, ran it. He loved systems that either worked or didn't, and he did not like the idea of an unknown sitting under his base. When Aisha brought the anomaly to him, his priorities were clear. This was a potential hazard as much as a science goldmine. "I don't care if it's geology or little green men," he told his engineers. "I care if poking it risks 147 lives up here." Aisha brought in one more mind, Dr. Hana Kuroda in Tokyo, a theoretical physicist who had spent a decade working on alternative gravity theories that most colleagues treated politely and filed away. Now, with a perfect gravity sphere under the moon, her inbox exploded. She knew the math of strange gravity, and she knew the danger. If the moon held some kind of natural exotic configuration, disturbing it could be like knocking on a warhead. They drilled anyway. Drilling into the moon meant chewing through regolith, pulverized rock and glass acting like razor-sharp dust, then potentially through ancient lava tubes, hollow basalt tunnels kilometers long. But the anomaly lay much deeper, tens of kilometers down, near the boundary between the crust and mantle, far beyond human reach. So Marcus lowered a quantum gravimeter string, a chain of small rugged atom interferometer pods, down a deep borehole to map the local gravitational field with extreme precision. As the string descended, the field pattern they reconstructed changed. Instead of the messy variations you'd expect from mixed rock densities, the lines of equal gravitational potential wrapped cleanly around a perfect sphere. And its center wasn't at the moon's center. It was offset toward Earth, almost exactly along the line connecting Earth and the Earth-Moon, barycenter, the point about which both bodies actually orbit. This thing wasn't centered on the moon. It was centered on the Earth-Moon system itself, like an instrument pointed at us. Marcus stared at the plot, twisting his wedding ring unconsciously. "This isn't random," he muttered. Somebody pointed this thing. Then came the strangest part. The lowest pod in the gravimeter string began recording an anomaly, not in the main gravity signal, but in the noise. Quantum gravimeters watch interference fringes. The tiny jitter in those fringes follows well-known statistical rules. It should look like pure quantum randomness. Hana zoomed into the noise spectrum and saw structure where there should be none. The distribution of fluctuations appeared to be modulated, patterns emerging from supposed chaos. "It's not noise," she whispered. "The fluctuations are being steered. Someone's writing in the randomness." Aisha was skeptical, but the math held. Whatever was under the moon had figured out how to encode information in the statistical properties of quantum vacuum fluctuations, a channel that no rock, atmosphere, or solar storm could easily block. They recorded this noise for weeks, terabytes of it. Hana built decoders, broke the pattern down, iterated as new data came in. When it finally snapped into place, she called everyone into the control room. On the main screen, a time series appeared. Peaks and troughs aligned with known events in Earth's history: global glaciations, mass extinctions, volcanic super-eruptions, major climate shifts. The signal tracked solar particle flux, ultraviolet intensity, and, incredibly, the changing spectral fingerprints of life: chlorophyll, oxygen, methane, in Earth's atmosphere. It was a continuous, compressed record of Earth's climate and biosphere, spanning roughly 4.5 billion years. A planetary black box. The vantage point? Not Earth orbit. Not some distant spacecraft. From inside the moon. If the data was as old as it looked, the recorder predated the moon's formation itself. The earliest entries came from orbits closer than the present-day moon. Later entries drifted outward over time, matching the moon's slow outward migration due to tidal interactions. Somehow, whatever this was had been tracking Earth before the giant impact that formed the Moon, and then had ended up buried inside the coalescing debris. It wasn't human-made, at least not by any humans we knew. Hannah laid out 3 scenarios. First, a weird natural object, a stable clump of exotic vacuum structure or negative pressure region, captured and encased by the Moon. Second, an alien artifact deliberately placed in near-Earth space eons ago. Third, a construct from our own future, sent back using unknown physics to sit and record our planetary history. Only one option had strong supporting hints. At the top of the data stream was a header, a structured preamble describing how the rest of the information was encoded. It didn't use universal constants or simple geometry like circles or hydrogen lines. It used the Earth-Moon system, ratios of the Earth and Moon's orbital periods, stable patterns of Lagrange points, geometric relationships unique to this two-body dance. It implied a designer intimately familiar with and probably living within the Earth-Moon system, not generic galactic engineers. And deeper in the record, nested apart from the main timeline, they found another segment with very different structure. It began with a star map, but the constellations were wrong, slightly warped. Using proper motion simulations, they realized why. It was our night sky millions of years in the future. Stars shifted along the paths we know they follow. Following that was a trajectory diagram, a dense object launched from future Earth orbit, executing a sequence of gravitational slingshots around stars that, by our clock, haven't moved into those positions yet. It traced a path back into the early solar system. It was a blueprint for sending something like the recorder back in time. The last frames switched to coding methods familiar to present-day humans. Base 10, prime numbers, bitmaps turning into images. They showed human figures, DNA structures, cultural symbols, equations, architecture, artifacts. The signature wasn't a personal name. It was a span of dates, pointing about 150 million years ahead of us. Some future descendants, post-human, digital, or something else, had apparently faced a big enough threat to justify bootstrapping a device backwards through space-time to watch over the entire habitable history of Earth. An intertemporal black box hidden in the most durable nearby structure, inside a small, geologically quiet, tidally locked moon. We hadn't stumbled on an alien probe. We'd uncovered a time capsule from our own far future. The message also contained a warning. In relatively accessible physics, it described an upcoming astrophysical event, a gamma-ray burst that would sweep near our region of the galaxy around the year 2150. Not strong enough to sterilize the planet, but enough to wreck satellite networks, strip some ozone, and kick our climate hard. The future engineers had used that event as a common timestamp, a fixed reference point. Both ends of the causal loop could identify. The recorder, it turned out, wasn't just a passive watcher. It had a second mode. It could function as a gravitational wave beacon, if supplied with enough energy. It could, in theory, send strong, encoded ripples outward, timed to coincide with that gamma-ray burst, acting like a flare back to its makers. Activating that mode, however, would mean pumping enormous energy into a structure whose inner workings we didn't remotely understand. Enough energy to potentially shift the moon's interior state, maybe even its orbit or rotation slightly, with unknown consequences for Earth's tides and climate. Marcus's instincts screamed to leave it alone. Catalog it, study it from a distance, but never flip any big switches. "I signed up to run a base," he said quietly, "not to roll dice with the Earth-Moon system." Hannah saw a different kind of risk. If the very existence of the recorder and its warning depended on some causal loop that included us responding appropriately, then refusing to act might erase the timeline in which the recorder was ever built, including the warning they'd just read. Aisha saw something else again, the culmination of human curiosity. A device built by our own descendants, entrusted to us across unimaginable time. A scientific instrument beyond anything we could dream of, aimed straight at our world. In the end, they chose a compromise. They decided not to trigger the recorder's full gravitational beacon mode. No massive energy surge, no attempt to shout back across time. Instead, they used the same subtle channel the recorder used to speak to them. Small modulations in quantum noise. At the very top of the ongoing data stream, they added a new, minimally invasive header. A small block of information encoded in the existing vacuum fluctuation patterns. It was simple, a marker of our present epoch, our level of understanding, a short mathematical "we heard you" appended to 4.5 billion years of history. "We received your message," it said in numbers only future physicists would love. "We're alive, we're trying." Then they backed away. The sensor string was retrieved. The drill was shut down. The anomaly was left undisturbed, humming in its own strange geometry. We used to look at the moon and see only scars and shadows. A dead rock, a mirror in our sky. Now we know it has layers, dust and regolith, ice and metal, human machines in its craters, and deep beneath, a silent recorder vibrating in step with a future we can't yet imagine. We went to the moon for resources. We found an audience. Proof that some version of us survives long enough to care about archiving every storm, every forest, every extinction, every civilization. Long enough to learn how to fold space-time so tightly that a message can slip from the far future back to the deep past. The real question isn't what we found beneath the moon. It's this: when we eventually become the people who sent it, when our descendants stand at that decision point, will they choose to send the recorder back again, closing the loop? Or will they decide that this time our story should unfold without a script buried under our own sky?